Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus, Lecture 4B, proving the power rule for positive integers and a few of the basic derivatives rules. So what we're going to focus on, so last time we focused on the definition of the derivative. We did a whole bunch of examples. And today what we're going to do is our first kind of shortcut to how to take these things with the power rule. Now, you can't use the power rule on the test. On test 1. You can on test 2, but not on test 1. But you may want to see some of these proofs, because some of the things on test 1, if you see this proof, it's a good practice for how to do things a little bit more abstractly with the definition of the derivative. So, as I said, you can't use the techniques on this. You can't use the results of today's lectures, but you can use the techniques, not the power rule itself, but the idea behind the proof. So let's go ahead and see what we're looking at. So again, last time we talked about the definition of the derivative. Today we're going to start with a little bit of the story of the power rule and their proofs, because there are several proofs for the power rule, depending on what your case is. So there's a power rule for positive integers, which we're going to talk about now, and then there's some other power rules as you make it more general. But our overall goal for today is to be able to do the power rule for be able to derive polynomials. So we want to be able to take this long polynomial and find its derivative without using the definition of the derivative, using some rules. So much like the limit laws, we'll be able to use these things to break things up. Okay, so we want to use the power rule for positive integers. Again, we're going to prove that. So what are the pieces we need? We need the power rule. We need a sum rule, because we need to break up this whole sum. We need a constant multiple rule, and then we're going to have to deal with this constant at the end, C naught. So we're going to need a little bit of a constant rule. And we'll talk a little bit about constants as a function versus constants of a number. So today is mostly about proofs. Next time, 5A is going to be about using them with more practical scenarios and things like that. Okay, so let's first talk about the power rule, because this is what, when you say, oh, I'm studying calculus to someone who's sitting in a bar next to you, this is what they're thinking of, right? They're thinking, oh, I remember how to take a derivative, and then they apply the power rule. So that's what, they do x squared and they come up with 2x, hence the joke, I don't always derive x squared, but when I do, I get dos equis. So this is the thing that people remember, right? It's kind of like the Pythagorean theorem. This is the rule that everybody will remember 10 years from now. So, but it doesn't work for everything, but it does work for a lot. So let's see some of the things. Just talk about this unified power rule for a minute. If C is some non-zero real or complex constant, for any x, if x to the c minus 1 is well defined, and there are a lot of places where it won't be, then the derivative of x to the c is cx to the c minus 1. A couple of things. C is constant. The exponent, or power, does not move. We're actually going to see this. We're going to see circumstances, and we're going to have something called the exponential rule, where the base is constant and the exponent moves. Here, for the power rule, the base is moving and the power is constant. That's the first thing. Okay. The second thing is that for positive integers, of course, this works. So here we've got an example. I already mentioned this before. The derivative with respect to x of x squared equals 2x. But I can also do it with things that I could put in a power form. Okay, so here's another example. Yeah. The derivative with respect to x of the cube root of x. Well, this cube root thing can be put in a power form. So I've got the derivative with respect to x. I should say power rule here. The derivative with respect to x, right? This the cube root of x is x to the 1 cubed. And that's something that you're supposed to remember from pre-calc. If you don't, that's okay. Get through test 1 and then come see me. Let's talk about this. Let's make sure that we're on board with this. And I will spend some time playing with these power forms and the different power laws during the next module. But this right here, I apply the power rule and I get 1/3 x to the 1/3 minus 1, which is 3/3. And that's the same thing as 1/3 x to the -2/3. And then if you want to simplify that more, that's going to be 1/3 to the cube root of x squared. So this rule is very powerful, but in order to get to that, again, there are multiple rules really, and there are multiple proofs, and they depend on each other in a certain way, okay? So it's really 4 theorems, okay? If c is a positive integer, this is what we're going to do today using the binomial theorem. There's one proof for that case. Then, when you have c as a negative integer, you need the original power rule, and then something called the reciprocal rule, which we're going to get for problem set 6. Okay. So that's what you need in order to prove it for negative integer, and you'll actually do it on problem set 6. If c is a rational number, as in p over q, where these things are, positive integers, or the top's an integer and the bottom's a positive integer, then you can prove that case using the chain rule and some implicit differentiation, and we'll do that in lecture 6b. Then if c is any real number and x is greater than 0, you can use logarithmic differentiation, and we'll do that in 7a to prove that case. So again, if c is needs to be non-zero, because if c is 0, you just have a constant, and we'll talk about that one today too. So that's sort of the plan. We're going to talk about the power rule, and then we're going to go through the sum rule, constant multiple rule, and constant rule. So in order to prove the power rule for positive integers, we're going to need some pieces, some old pieces from high school. And the first of these is the binomial theorem. So this is Pascal's binomial theorem. And the binomial theorem, believe it or not, is one of the big pieces of glue in mathematics. It connects simple ideas with from counting, with algebraic structures involving numbers that are interesting, to analytic structures like calculus. So it's actually, believe it or not, this simple little Pascal's triangle theorem is one of those deep pieces of mathematics. One could say the proof of God pieces of mathematics, right? Because it shows that there's a deep underlying logical structure to numbers in general. So I have a video that I've done for discrete. I'll link it in the description if you're interested in the binomial theorem and how to prove it. There's really beautiful arguments involving a deck of cards that show the binomial theorem, but it's a very hard proof. It's a simple proof, but it's got a thing where you just have to go, oh, I get it, kind of thing. It's a hard proof. It's one of those very simple but very hard proofs. So if you're interested in it, please watch it. I'll link to my video. There's also wonderful videos on proving the binomial theorem online. And they're all based on counting principles, which is really interesting. So let's just state it right now. N is a positive integer. Then a plus b to the n equals this expansion here, this sum. N choose 0, a to the n, b naught, plus n choose 1, a to the n minus 1, b to the first, plus blah, 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 plus at the very end, n choose n, a to the naught, b to the n. So for example, x plus h cubed here is going to be 3 choose 0, x cubed, plus 3 choose 1, x squared, h, plus 3 choose 2, xh squared, plus 3 choose 3, h cubed. And this 3 choose 0 equals 1, as does 3 choose 3. 3 choose 1 equals 3, and 3 choose 2 equals 3. And the fact that this is connected with something combinatorial like these choose, right? We actually, it wasn't. If you take an undergraduate course in discrete math. Also, they'll talk about this combinatorial number. And the fact that the combinatorial numbers are the same as the numbers in the binomial coefficient is why Pascal gets this thing named after him. Okay, he's not the first to propose this. The Chinese understood it way before him. He's not the first to talk about combinatorial numbers, but he's the one that connects this idea of combinatorial numbers to this theorem about this combinatorial thing about objects and gambling to this beautiful theorem about numbers. And it's really one of those beautiful things in math that you ought to see. Anyway, let's talk about what this n choose k thing is. N choose k denotes the number of ways to choose k items from n objects where the order doesn't matter. Think a deck of cards. Okay, how many ways are there for me to deal 5 cards from a 52 card deck? So if I come out here and I go, okay, I shuffle the cards and I give you 5 cards. 1, 2, 3, 4, 5. Okay, how many different possible hands of poker or hands do you have where the order doesn't matter? So for instance, this right here is a pair of 2s, right? It's 2 2s with the 5 of hearts, the 9 of spades, and the 7 of clubs. Now, this hand is the exact same hand as this hand, which is the exact same hand as that hand, right? This is just 5 cards, and I don't care about the order I got the cards in. It's just 5 cards, okay? So the number of ways, or the number of possible ways I can get 5 cards, right? All the different sets of 5 cards, all the different 5-card subsets of the set of 52 cards is called 52 choose 5. That's the number of ways for me to be dealt 5 cards, right? There are 4 royal flushes in there as part of that, but there are a whole bunch of other combinations, busted flushes and all these other things where I didn't get anything. Okay, so 52 choose 5 is the total number of possible 5-card deals from the deck, where the order doesn't matter. Okay, now, how many ways are there for me to deal 2 cards from this deck? And that number, and I don't actually care what the formula for this number is, by the way. Okay, I want the number to be 52 choose 5, not the number when you work it out as an integer. No, 52 choose 5 is the concept. I want to keep that as the number. Again, that says how I got the number, so that's more important. Now, 52 choose 2 is the number of ways to get 2 cards from this deck. Okay, so I could have gotten the 5 and the 9, 5 of hearts, 9 of spades, like I did here. Or I could have gotten, anything from this deck here. Excuse me. Yeah. The 3 of spades and the 4 of hearts. So, again, order doesn't matter. Ways to choose cards. There are 52 ways to choose a single card. Everyone on board with that? I got 52 cards. There are 52 possibilities for the card I got. So here I got the ace of spades. Oops, I only meant to get 1. The ace of spades. All right. There's 52 possibilities for the card I get. So 52 choose 1 is just 52. Now, there's one way for me to get handed the entire deck, right? Because again, order doesn't matter. So if I deal all 52 cards from the deck of 52 cards, I'm going to wind up with 52 cards. All 52 cards, and there's only one way to do that. I hand over all 52 cards. This one's a little strange. In the exact same way, there's only one way to deal 0 cards. Okay? I give you no cards. There's only one way to do that. So 52 choose 0 is 1. Okay? That's a little weird. You think, oh, there's 0 ways. No, there's one way for me to give you no cards. I give you no cards. One way. All right, another way of thinking about that is there's one subset of 52 of the deck with no items in it, and that's the empty set. So if you're having trouble with this idea of ways to deal cards, think about the fact that the empty set is the only 0 element subset of the deck of cards. Okay, so let's generalize this, and we need 3 things. We actually only need 2 of these. N choose 1 equals n choose n equals 1, and n choose 0 equals 1. Okay, so those are, and we need n choose 1 and n choose 0 for this little fun game that we're about to play when we prove the power rule. Okay, so let's state what it is we're doing. So that's what we're doing. We're just proving the power rule for positive integers. So if n is any positive integer, then the derivative with respect to x of x to the n equals nx to the n minus 1. Let's do a couple of examples with their generalization. So let's look at x squared. Okay, so let's look at what happened here. So overall, when we did the thing, we used the h definition of the derivative, and we ended up with the x's. So I had this x plus h squared, and I had an x squared that canceled. So I'm sorry, not the whole thing. I had an x plus h squared, and the first term of that expansion was x squared with no h. And that canceled my x squared out on the top. From what was left, everything that was left had an h term in it. So I factored out the h, canceled it with the bottom to get 1, and then I was left with a term with an x in it, no h. Right? I was left with one term with no h, and all the rest of the terms had an h in it. When I went to 0, I got 2x. So let's say that again. Okay, so again, I had something. I got when I expanded the x plus h, I got an x squared term that canceled the negative x squared. I factored the h, so everything that was left now had an h on top. Everything in the top now had an h in it. I factored the h and canceled it with the h on the bottom. That left me one term without an h. When I directly substituted it, it's the only term that survives. So that's the only term without that survives when I do the direct substitution. Okay, so that's how we dealt with that. Let's do another example. Okay, so I did sort of the same thing I did before, didn't I? I used the h definition of the derivative. I had x plus h cubed. Now, let's look at what happened again. I got an x cubed. I've got the exact same direct instructions here, but let's modify them. So here are the instructions I had. All right, so let's modify our instructions. So I had an x cubed instead from expanding x plus h cubed, which canceled the negative x cubed. Everything else had an h in it. I factored the h and canceled with the h on the bottom. That left me with the 3x squared term with no h in it, and another term and with h's in them. Those terms went to 0 when I directly substituted it, and I was left with the 3x squared. So basically the entire same set of directions, except I had to change the plurals of the words and change those to 3's, and then change this to a 3x squared instead of just 2x. So we can sort of see how the proof is going to go. And notice also, I didn't need the expansion. I didn't need to know what 3 choose 2 was and 3 choose 3 because they're both going to be multiplied by 0. I know they're numbers. They're not infinities. So when I stick in h, those two terms are going to go away. And the only one I needed was 3 choose 1. And 3 choose 3, right? Which is 1. Okay, so let's try to prove the proof goes the exact same way. So let's prove it. And that's going to be my strategy. So what is it I want to show? I want to show so kind of a long strategy and introduction. I probably didn't need to write all this. I could have probably just said strategy. Use h definition of the derivative and the binomial theorem on x plus h to the n, and then obey the consequences, right? Everything else just kind of flows from those two directions. So let's go ahead and prove it. Now, here's an opportunity that I might be a little confused about. I've just factored an h out of everything here. So you might want to include another term. You don't have to. Notice I did this 2 minus 1 business. You don't have to. You could just write h to the first. I would, however, leave something in there. So people understand that what happened was you factored out an h, and that left me with h to the first, blah, 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 h to the n minus 1. So just a thought. You may want to clarify. You could also say right here, factored out h out of each term. You might want to say that you're doing here, expanding those two binomial coefficients. You just need to be able to communicate to someone who doesn't quite understand / believe what you're saying. So however you decide to do that, it's up to you. I like to write the binomial. I like to write things above my equal signs. I could also have a little running commentary on the right. That's something that a lot of people that teach geometry like to have you do is, you have your steps on the left, and then you have your commentary about your steps on the right. That's still sort of taught in high school sometimes. So if that's comfortable to you, go ahead and do it. You figure out what works for you as long as you're communicating in neat. As long as someone can follow your flow, that's what you're looking for. Oops, there shouldn't be a limit inside there. I got rid of it. Half a point off for me. Well, now I've fixed it, so, Okay, so what I did was what I said I was going to do. And that's kind of there's details, but I didn't need to be this detailed. This is a very proof. But I could have skipped a few. I could have definitely, this step right here, I could have ditched one of these, certainly. Okay, I mean, this one and this one. I could have definitely ditched one of those. I can't ditch the whole DS step, but I could have gone from here to here. This, I could have probably gone, if I kept this DS step here, I could have skipped that one. I can't really skip 2 steps in a row, but I could have skipped this one by doing the cancellation and then the factoring right here. All of those things would have been legit. I just, I can't skip 2 of these in a row. And also these little helpful things. Again, if you want to write that on the right, if that's what you're comfortable with, go for it. So that's the idea behind the proof. Okay. So now we have the first piece that we need for our polynomials. There's the power rule. Now what we're going to do is do the sum rule. Theorem. Okay. If f and g, and notice that these are rules instead of law. Who cares? It's just, we usually say limit laws because it kind of has a little alliteration in it. And we have derivative rules because we don't have a D word for rule, really. I guess derivative decree would be better. But, we say limit law. And so we have rules for the derivatives. What do you want? So all it says is the derivative of the sum is the sum of the derivatives, as long as the derivative of f and g both exist. So let's just prove it. And the strategy for the proof is what we'd expect. There we go. I use s of x for sum. It took me a minute. What am I going to call this? Because I don't want to call it h because I'm about to use h as a variable. And this proof is just going to flow right off the limit law. So this piece right here, s of x plus h. So s of x is f of x plus g of x. So that means s of x plus h is, by the definition of s, f of x plus h plus g of x plus h. And then s minus f of x is minus f of x plus g of x, all over h. And my goal is to get to 2 pieces. So my final piece of my proof, okay, should look like f of x plus h minus f of x over h plus g of x plus h minus g of x all over h. Okay, so let's just write that over here in little commentary. And I can actually put that in my introduction if I want to. Okay, because this is what I want to show. I want to show that this side right here, this thing right here, equals this bit right here. Okay, so now that I have that, what I'm going to do is I've got this whole thing. What I'm gonna do is I'm gonna reorder the top. I'm distributing the negative and reordering the top. Okay, now I'm gonna break the fraction into two pieces. You know what? I'm not gonna skip that step. I'm gonna actually do that step. Right, so I distributed the negative and then I just reordered. So what I did there was I used the sum law. Once I have the sum, right, I have an h on the bottom. I split up the fraction, and I've got two things with an h on the bottom. Then I applied the limit law to break it up, the sum. Once I broke up the sum with the limit law, this right here is the definition of f prime of x, and this right here is the definition of g prime of x. And again, there are things I could skip. Right, I could have probably ditched this step. Or I could have ditched this step if I kept that step. I could have ditched this step here and just gone straight to here, right? Because here, once I have this, the ordering and then the breaking up of the fraction, I could skip that. Especially if I did a little highlighting or if I wrote reordered and broke up. Here, the sum law step, I really couldn't skip. I needed something. This step is kind of important because this is the step right above the sum law. This step is obviously important, but I could have done a little thing and gone this equals f prime of x and a little thing right here that says this is the definition of g prime of x. Okay? I could have also written a little commentary here. Right? I could have done this. I could have written some commentary on the side. There's a lot of different things I could have done to just say what I was doing. So again, remember the key here, the point, is that someone who didn't quite understand the problem would be convinced by your argument. So that's the sum law, the sum rule. Now we need the constant multiple rule because we want to get rid of, so now we have the ability to break up all of these pieces when we take our derivative. Now we need to pull the constants off. So I'm not going to prove this. You can prove it for yourself. Indeed, it's a question. I think it might be a question this year on the bootleg. It might not have made it, but this is the theorem. And by the way, it's in the notes. So if you go to the notes that are in the description, I actually show all these proofs in the notes. So here the rule just says, if I've got a non-zero constant and a differentiable function, then I could just pull it off the derivative. So here's the example. Right? The derivative with respect to x of 6x squared is going to equal 6 times the derivative with respect to x of x squared, which is going to equal, now I'm going to use the power rule, 6 times this derivative here, which is 2x to the 2 minus 1, and then I'm going to simplify as just 12x. Okay. So all the constant multiple rule says is that I can pull constants across the derivative, just like the limit law, and indeed you prove it just like the limit law. Okay, we need one last piece when we want to deal with the definition of, when we want to deal with polynomials. And that's what the derivative of a constant is now, or of a constant function. So there's something here that I want you to keep in the back of their mind, because sometimes it confuses people. And it's one of these ideas that is kind of simple but hard. You have to kind of abstract away it just a little bit so that you don't get confused, and you don't confuse numbers with functions. So for up here, when I had the constant multiple rule, here C in this case is being treated like a number. Okay, so the rule says that if I have a number C in front of some differentiable function f of x, I could pull the C. Here C is being treated as a number. But here, when I have f as the function so that for any x, f of x equals 2, 2 is actually this is the function 2. F itself is not a number, it's a set. It's the set of x comma 2. It's the line y equals 2. When I graph this function, I actually have a function, correct? So, right, it's not just 2, right? It's the set that includes -6, 2, -4, 2, pi 2. It's this giant set of numbers. It's a function. Okay? And again, I want to distinguish when I'm thinking of functions as numbers versus, I'm sorry, when I'm thinking of constants as numbers versus constants as functions. So this is the derivative not of a constant as a number, but the constant as a function. When I'm thinking about a constant as a function. So I just want you to be aware of this in the back of your head, that this right here is a function. This C right here, when I'm talking about the constant multiple rule, I'm treating the constant as a number. But when I treat the constant as a function, the derivative is different. Okay? So, this is notation I never want to see again. Let C be the constant as a number. Then the function constant C, with this little notation, equals x comma C for x and r. So it's my line. Whatever my C is, right? So here is my C dragger here, and I'm going to set C to be 3.2. Now, CON, I had to use K here instead of constant C of X, but pretend this says CONS like I did on this. This KC of X is the equals C. This is the function. So when I take the derivative of this function, I'm going to wind up with 0, because this is a line, and the slope, the derivative of a line is the slope of the line. This particular line has a slope of 0. Okay? The other way I can think of it is that, you know, I have a function that doesn't change anything. Derivatives measure change. So because there's no change in y, when x changes, dy over dx always equals 0. What's the change? Nothing, right? As x moves from 1 to 1.5, there is no change. It's still outputting 2, 2, 2, 2. So I don't change as I move along in the function. It's not that there's no slope, there is a 0 slope. Okay? Again, there is 0 slope. Here I'm 2, here I'm 2, here I'm 2, here I'm 2. I'm always 2. And if I'm always 2, everybody gets a 2. Everybody gets a 2. And there's no change from one thing to the next. It's just 0 change. Right? 2 minus 2 is 0, because that's the change in y. And I don't care what the change in x is. The change in y is 0. So 0 over anything, right? Any non-zero change, right? In the x value, I'm changing a little bit in x, but not in y. And I'm going to have 0 over some number, you know, and I'm going to wind up with the change of 0. So that's the constant rule. But remember, constant as a function. And I never, ever, ever, ever want to see this notation again. I just want you in the back of your head to go, is constant here a number or constant here a function? Is constant here a number or constant here in a function? I just want that screaming at you in the back of your head. Okay? So the constant rule says that the derivative of the constant function is 0. No, that is not this. Here with the constant multiple rule, constant is a number. Let me write that. Here, C is treated as a number. Okay, so when I take the derivative of something times f of x, don't go 0 times f of x. No. This is c times the derivative of f of x. Here, the constant is being treated as a number. Here, when I've got a constant all by its lonesome, it's all by itself. It can't survive all by itself. Again, a c cannot survive all by itself because then you're treating it as a function. Okay? So, when I take the derivative of something like this, c is all by itself. Okay? And I can see that c is going to be all by itself because I do this with the sum rule. It's all by itself.
All by myself. Don't want it all by myself anymore.
And then it dies. Okay? But compare that to the following. Okay? If it's not all by itself, it survives. Right here, it's mated with x through multiplication. The sum rule here, the sum rule can't deal with x. You know, the sum rule here doesn't carry the c. It doesn't mate the x and the c, right? Because all I do is I break them up and I've got the derivative of c all by itself. So here c is being treated like a function. Here c is being treated like a function. But here c is a number because it's being multiplied by x. Okay. So just bear in mind in the back of your head that the derivative of a constant as a function is 0. Okay. Now, again, I never want to see that notation again. I just want it in the back of your head. Is c a constant or is c a function? The constant function or the constant number? Just keep it in the back of your head. All right. So here's the formal proof. Let f of x equal c. Okay, then f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, f of x plus h is c. So I've got the limit as h goes to 0 of c minus c over h. Now, don't sub in the 0 yet. That's going to give me the limit as h goes to 0 of 0 over h. Now, notice, 0 over h is 0. There's no 0 over 0 here. Right? I don't want to sub in. Now, this right here, this limit sign is still here. So if you're wondering, Scott, why don't you want to, I wrote a limit sign that wasn't needed. Why did you dock me? Here's why I docked you. This right here is a limit sign that's still needed. I have not used a rule to get rid of the limit. I've got limit h over 0 of 0. Now, this right here, the limit of the constant, now I get rid of my limit. I apply the limit rule of a constant. I never subbed in h. Notice that. I never subbed in h. I've got the limit as h goes to 0 of 0. And now I apply the limit of the constant rule, and it stays 0. Right? The limit goes away, and I've got a 0. So that's how you do the formal proof of the constant rule. Again, it's a little confusing because you've got the limit as h goes to 0 of 0 over h, and you're like, well, that's 0 over 0. No, it isn't. It's just 0 because I can get rid of the h without subbing in. Okay? There's no subbing on here. I've still got the limit as h goes to 0 of 0. Now I apply the limit law, and I wind up with limit. All right, so now I have enough pieces to do the derivative of the polynomial. So, for example, I've got f of x squared plus 3. F prime of x is going to be, I'm going to break up the sums. Then I'm going to pull off the constant. Then I'm going to apply the power rule. I'm going to use the constant multiple rule here. Then I'm going to apply the power rule. And then I'm just going to use the limit of the constant to get rid of the 3. Okay. And you can generalize that as you will for the full proof. And I think I already did that in the notes. Okay. So today we proved the power rule and we proved a bunch of the little derivative rules. Next week, we're actually going to spend a lot of time, after the exam, we're going to spend a lot of time playing with them. Okay. So, we're actually going to do practical hands-on things. And we'll do it in a problem set, and then we'll do it in the in lecture. So the next time, what we're going to do is we're going to talk about the other derivative rules, the derivative sign, which if you did the chaser packet, if you did the chaser packet for number 3, if you got assigned to it. So sometimes when a class doesn't have skips a class during a week, like Labor Day, Memorial Day, that sort of thing, we skip the chaser packet. So that sometimes happens. So if you're in one of those without the chaser packet, you might want to go ask me about the chaser packet, but you won't get any credit for it because, we only had one class that week. If you did have the chaser packet, you already proved the derivative of sine. Anyway, so we'll do sine, cosine. We'll do some other derivative things like c to the x, which is different than x to the c, and we'll do some of the other ones. So we'll do some more basic derivative laws next time. Good luck on your test, and I will see you next time.